We've seen how to represent Boolean circuits, but to have a computing model, we also have to define how they execute.
The book has a definition that does this. We're going to develop an alternate one. One way to think about a circuit, and this is very natural if you think about circuits as hardware, the edges are really wires. They carry values. They're not unlabeled. The edges are unlabeled. They're just connections. Well, for real, they carry values. Well, not for real. This is a model. But if we think about how a circuit works in hardware and our intuitive thought of how it executes, we can think about those edges carrying values. They carry values that represent the bits in the circuit. That means we can define a function that's going to map any edge to its value. This is like a label of a node on a graph, but now we're labeling the edges with their values. But I've added one little wrinkle to this. We might not know the value. This is a symbol sometimes called bottom, but it's used often to mean undefined. If we think of this as a function, we're saying, well, we're turning a partial function into a total function by saying for the things where it's undefined, we're going to use this special symbol to represent undefined. So in that sense, it's still kind of a partial function. It's not always defined, but it's going to make it easier for us to work with it if we can explicitly say when it's undefined, its value has this special value. But if it's defined, it has 0 or 1. If we have that definition, then it's easier to talk about the output. The output is what are the values on the special wires that are the output wires. And we're going to define the output of the circuit now as the values on those wires where the yi value, the ith bit of the output, is the value on the wire from some gate to yi. We're numbering all the inputs and outputs, but these special output vertices always just have 1. It's maybe unnecessary, but it's to be consistent. Of course, for this to make sense, for the output to be unambiguous, there better only be one edge from a gate output to a circuit output. If there was more than one edge, then we don't know what the value means. Certainly, we haven't done anything in this definition to say there can't be, but we better say to be a valid circuit, there better only be one edge. Have we defined a model of computation? Do we know how to execute a circuit now? What don't we know? What do we need to do? Yeah. We've defined our output now in terms of the wire labels. We haven't defined W. W is the function that goes from edges to values. And we defined output in terms of W, but we haven't defined W. We just made it up. We have to explain what W means. So how do we define W? Any ideas how to define it? So are there any special edges that we need to know the value of W for? Yeah? Yeah, good. Right, the input edges, we better have some magic way to know their value. The circuit's not going to tell us their value. They came from outside. The input's actually a gate. So the input is some gate that is labeled input. It doesn't have any edges into it. It has an edge out of it. We've got to know that the value on any edge where it's from an input to anything else, we better have a way to get that value, right? That's from outside the circuit. The point of the circuit is it can take an input from the outside world or our mathematical outside world and do some computing on it. So those are going to be special. That's going to be defined by some input function that tells us what the input for that gate is. Everything else better be defined in terms of things that are inside the circuit. Right. So how do we define the other wire labels? When we start, we better know the input. The others we don't know. Well, good news. We have this special symbol. That's what we define them as. We define W on edges. It's more useful to think about as long as the value from the input to the output doesn't change. If we have an edge like this, what matters is that value. So we can define it just on the outputs. Part of the awkwardness, or at least one of the difficulties, these edges are connecting outputs to inputs, and we defined our wires. Wires connect outputs to inputs, right? If we think of physical wires in a circuit or edges in a graph, But we know the value on the wire just from the output. And it's always going to be the same. If the same output is connected to different things, all of those edges better have the same wire label. So we're going to change, instead of this, we're going to just define the val function. We can define the wire value in terms of just whatever the first gate in the pair, that's its value. So initially, all the values are bottom, unknown, except for the ones that are inputs, which get their value from somewhere outside of the circuit. You're going to get their value from some function input that has to be defined. If we're going to actually get an output from the circuit, we've got to get real values that aren't the undefined values on the output gates. So we need some way of making progress. So how do we make progress? Yeah. Excellent, yeah. Any gate that has all of its inputs defined, we can determine its output. And its output depends on the type of gate, and this is where you get into the question of are the gates total functions, or how do we define what gates compute? But they definitely can't compute until they have all their values. Once they have all their values defined, any gate, once its inputs are defined, we can compute its output. Do we know there are any gates that we can compute outputs for? Yeah. So certainly, without constraints on the circuit design, we do not know that. With constraints on the circuit design, we would like a well-behaved circuit to say every gate is connected to other gates, and if they're in topological order, eventually the gates before it are going to know their values. That's the intuition that we want this definition to capture. Here's the way we're going to write that. We're going to say, here's our initially. It should make you a little bit uncomfortable that trying to provide a mathematical definition here, and we're using something kind of like a while loop, which looks a little more like code. So that should make you a little uncomfortable. We would have to be pretty careful to make sure that, yeah, this is well defined what we're doing here. But it's actually just saying, well, we're going to keep doing this as long as we can, which is easily defined mathematically. That doesn't depend on any particular programming language way of implementing a while loop. We're just saying as long as there exists some edge in our set of edges, so as long as we can find some edge, it doesn't say which one, pick any edge that satisfies this property that currently we don't know its output value. If we didn't have that, what would go wrong? At least the way we've defined it. Yeah, so this gets into, like, if this was sort of, maybe if we had a careful mathematical notion of what while meant, it would be okay, because it doesn't matter that we can go forever. But it's kind of a lot more comfortable to say, well, we're going to be done when there are no other edges that are missing their label. We're going to look for a gate that doesn't know its output, and all of its inputs are defined. Any gate we find like that, we can evaluate. And we're going to evaluate it by applying whatever this function is. Although we've been calling the labels, things like input and or and not, they're functions. So we're going to take whatever the label is, which is a function, and apply it to those inputs. And now we know the value of the output of that gate. Are we happy with this definition? What are the things we should want to know about a definition like this, especially one that's got a while loop in it? Yeah. Yeah. So we would like to know, for this to match our notion of a Boolean circuit, we want it to finish, and what should be true when it finishes? Yeah. We should have the correct output. Well, correct is defined by this, right? We're defining what it means to execute, but we have some notion of what it should mean. So it should produce the output that we expect. This is just putting that a little more formally. We've defined execution in terms of the output that's produced. That's the result of completing that definition of assigning the values to all of the wire labels or the outputs of gates. Before we try to see that it behaves well, what would it mean if it behaved badly for some circuit? So suppose there was we complete this process, and there is some yi that's value is still undefined. Good, yeah, it means it's a bad circuit in some way. So it's certainly the way we've defined circuits. If we don't have any constraints, there are plenty of circuits. Let's draw a simple one. If this is our input and our output is this, there's no connection. It's never going to be defined. What's another thing that could go wrong with this without any other constraints? Could we have a fully connected circuit that still doesn't evaluate correctly? What could cause that to happen? Yeah, we could have cycle. If we have any cycles, no matter how much they go through, if they end up having outputs that depend on inputs that depend on outputs of the same gate, we're never going to end up with a defined value. In some sense, this is kind of a nice property. At least it's a nice property. Instead of saying we only allow circuits that are well behaved, say we've got a definition, we've got a computing model, and if you give it a circuit that is bad in some way, it's going to not blow up. It's going to give you something with this definition, but it's going to give you an undefined output. Right? That's kind of desirable. Yeah. So it doesn't have a value computed unless all of its inputs are defined. If we had a circuit like that, this value is never going to be defined because we can't get this output until this input is good, and we can't get this output until both its inputs are defined, and they all start undefined. So we're never going to define those wires.